enol formation would be to protonate the oxygen center, right? To protonate the oxygen center. And this reaction does not work very quickly at all anymore because that oxygen of the carbonyl oxygen, is less basic than the original carbonyl oxygen was. So if I were to label this OA, this guy OB, right? OB is far less basic, nucleophilic, than OA was. The original one had, good basicity, was able to pick up that proton with relative ease. But now that we have a halogen at the alpha site, we actually are slowing down the reaction by far, and hence, we actually work this reaction then for monohalogenation, okay? Whereas when we did this reaction a la the iodoform test, so we did something like I2 in NaOH, right? We actually got many halogens onto that alpha site. So we were able to get to something like this, right? This kept going and going and going, kind of like the Energizer Bunny, right? It kept going and going and going because in this case, we now have the ability to create the enolate with much more ease than initially, okay? You look at the very first intermediate, I've gone all the way out here, but the very first intermediate was something like this. And now, in order to create another halogenated product, you would need to create the enolate. Well, this enolate is very easy to create in these conditions, much easier than original, because the fact is that pulling electron density toward the I- is going to stabilize the conjugate base that's created there. Okay? So, in acidic conditions, the ability to form the enol slows way down after the first halogen addition, whereas in base conditions, it actually speeds up after the first halogen addition. It speeds up even more after the second halogen addition, okay? Because you're changing the pKa of this hydrogen. Does everyone understand what I mean by this? Okay, so then, what? There's no eraser? That'll be good. All right. So then, we know that the last step in the iodoform reaction was to actually now attack at the carbonyl center to create a tetrahedral intermediate. So when you look at your tetrahedral intermediate, this is what you have, okay? The very last step after you halogenate at that methyl site, trihalogenate, now it's completely halogenated, is now you've ramped up the electronegativity here. The OH attacks at that carbonyl center. You create this tetrahedral intermediate. And as we know, every tetrahedral intermediate wants to collapse. And when it collapses back down, this group can leave. Okay, it's stabilized by the fact that it has 3 iodo groups on there. Stabilizes that anion, and when it leaves, you create the carboxylic acid, which you should note is 1 carbon shorter, right? Your backbone is 1 carbon shorter. You took off that methyl group, right? This is a carbon loss reaction, loss of carbon, right? We always talk about carbon adding. The carbon loss is something you should be looking for in synthesis as well. In this case, your leaving group will deprotonate and drag via acid-base chemistry this reaction forward in terms of pKa arguments. Okay? Yes?
Does that mean there's a second edition of the OH group? So the carbon wall edition, or is it still
Okay, that's a good question. As you go from the enol to the enolate, you actually aren't using up any OH if you follow that mechanism. Because as you protonate at that oxygen center, when you create, you recreate OH minus. So you actually aren't utilizing any of the OH minus until you're out here. The
would you like us to assume acid workup in terms of an exam or homework assignment?
So without acid, this is the end product, right? If you add some acid in, this is when you can collect your neutral species.
Right.
Yeah.
So
But you know this is the end. Okay? All right. So the last step, or the last piece here, in terms of the alpha carbon, is alkylation. Okay, is alkylation. And you already have a reaction that does this, right? A la the homework. You had a reaction that would alkylate, and that was through an enamine, right? 1 second. Get there here. So you know that you can take something like this and add create this. You can alkylate from here via an SN2 type reaction. Which in essence would collect that R group. And then via H3O+, so this is after step 1. After step 2, you would get back to your ketone. So this is through an enamine. There's some things you can note. First and foremost, which site do you always alkylate? The less substituted site, right? So that's number 1. Right, so this is one way to do it is through an enamine. But to note, this is always on the less substituted alpha site. Okay? Anyone note anything else here? Bless you. The conditions we use at all times are acidic, right? So that could be important to us. Okay? Acidic. If you had any functionalities that were acid sensitive, you'd need to be careful there. Okay? So that acidic conditions might be important to you. One thing we didn't talk about are the types of RBRs that you could do here. Generally, these are sort of allylic and benzylic positionings where the bromination is or the halogenation is. But I don't think we're not necessarily going to test you on that. But that is another piece in terms of trying to understand why there would be more than one mechanism to do this alkylation piece. Okay. The other is to use LDA. So this is one way. The other way is to use LDA, and LDA can be used, as we talked about last week, in terms of getting either the enolate that is more substituted or the enolate that is less substituted, right? We said with LDA, which is a strong base, I'd be able to get 2 different enolates. If I use LDA at low temperature, which enolate am I going to get?
Kinetic.
The less substituted one. That's exactly right. So I'm going to get this enolate out, the less substituted one. Okay? And now this would allow me, because if I look at the resonance structure, I've just drawn the most stable one in. Sometimes I draw the most stable, sometimes I draw directly what results. But in this case, this would then be your nucleophilic site, right? This less substituted carbon. And you can halogenate, or you can alkylate there. So that's now the same thing as the enamine, though, right? Because it's the less substituted side. But we don't have any acid here, right? So if you had a base-sensitive functionality, you need to be careful with this reaction. So we sort of, it's the yin and the yang developed for, whatever other constituents or substituencies you have in your molecule, the important piece of what you use. Yeah.
How did you get back to a ketone with the enamine?
So in this case, this was step 2. So this was the end of step 2. So step 1 will halogenate, and this was my intermediate. And then step 2 is to use H3O+, right? Which is going to disentangle this back to the ketone. And so we can alkylate here through the less substituted enolate, right? Or I can go for the more substituted enolate. And that would be to do this usually at room temperature. You don't necessarily need to heat this up. But at room temperature, you can create now, I'll draw the resin instructions differently here, you can create the more substituted enolate and therefore alkylate at that site. Does everyone understand what I mean by this? Is everyone okay with this concept? Okay. All right. Any other questions about chemistry at the alpha site? Okay, good. So, we're going to move into aldol condensation then, which is working from these enols and enolates. All right, so here's just a general outline of what we're going to talk about here. Okay, depending on how far you go, the product of these aldol reactions can stop at an alpha beta or a beta hydroxy ketone or aldehyde. That would be the first step along our path. Or if we heat the reaction up just even a little bit, we generally do these in base conditions. If you heat it up a little bit, you can actually get then an alpha beta unsaturated ketone or aldehyde. Okay? So what's the difference here, right? A beta hydroxy ketone or aldehyde looks something like this, right? That's a beta. This is the alpha. A beta hydroxy ketone or aldehyde. It's obviously a ketone. Or I can have an alpha beta unsaturated ketone or aldehyde. This is alpha. This is beta. That's an alpha beta unsaturated ketone or aldehyde. Okay? So every aldol proceeds through this for sure. Again, if you heat it up, more often than not, you wind up with your alpha beta unsaturated ketone or aldehyde. Okay? Through loss of water, beta elimination, similar to what you've seen before. So in this case, we're going to be looking to generally create these through the end of the aldol condensation reaction. Okay? So whenever we talk about these condensations, there's a few things that we talk about. One is self-condensation, one is directed condensation, and the third is an intramolecular condensation. Okay? The difference between self and directed generally means the self-condensation, aldol condensation, means I take one molecule and I'm condensing it on itself. Whereas directed means I take one molecule to create a donor and I add a separate molecule that is an acceptor. Okay? So that I guess you can call that as well mixed aldol. Directed or mixed aldol is how we would talk about that. Okay? Now, here's the premise. We'll start with acetone here. When I add OH minus, because this is what I would add to do a self-condensation reaction of the aldol variety, I would add OH minus. That's generally what we add, sodium hydroxide. You need to add a base. need to deprotonate. When I add OH minus to this reaction, you've already seen this. I create this molecule, and H2O. This is one of the acid-base reactions from your homework assignment last week. So here is the acid-base reaction there. And what I know is the pKa of the acid on the right is 15.7. And over here is 16 to 20. So this arrow could sort of be an equilibrium arrow, or it could be shunted a little bit more to the left than it is to the right, but not much. In general, we're at equilibrium. Does everyone see what I mean? So at equilibrium, I would expect that in the reaction pot, after the base has been added, I'm going to have 50% of each of these molecules, roughly, okay? A 50-50 mix. And what I actually get a 50-50 mix of is a donor, what I would call a donor. A donor generally means the nucleophile. This is the nucleophile because it has an electron pair and a negative charge. Specifically, my nucleophilic atom is the alpha site, right, of this molecule. And the other 50% of the population is an acceptor, right? I have an acceptor molecule, aka the electrophile. And the electrophile in this reaction is the carbonyl center, right? So I have a donor, the alpha carbon, and I have an acceptor, the carbonyl carbon. And I have a 50-50 mix of each. So I'm expecting some self-reaction, self-condensation, where the donor will actually react with the acceptor site in the non-deprotonated populations of my acetone, okay? So the reaction generally looks something like this. I take this carbon, which is my donor, and it reacts at the acceptor site. As we've seen before, I have nucleophilic attack at the carbonyl center. The carbonyl center has got to move its pi electrons up onto the oxygen site. Okay? So then we look at what we have on the other side. Okay? These are my two CH3 groups. See, I'll label them. This is A and this is B. Okay, so those are my two methyl groups from the acceptor molecule. And here are my three atoms from my donor molecule. Specifically, this site, right, is my nucleophilic site of the donor molecule. Okay? Take a minute to orient yourself here. Generally move the two R groups of that acceptor sort of just out of the way as we push the donor molecule in. So currently I have two methyl groups that were part of the acceptor. Yeah?
Is that a racemic mixture?
Is it a racemic mixture? So in this case, you can't actually say whether it's going to attack to create R or S. So yes, that's not going to matter when we get down to the alpha beta unsaturated. Okay. So as we consider collapse back down, okay, collapse back down, we would have to push out this leaving group. The one that would leave is likely this guy here. And there is definitely some reversibility associated with this. Okay, it moves mostly to the right, but there's definitely some reversibility associated with this. You actually do see a reverse aldol in glycolysis. You should try and go check it out. That's been an exam question in the past. You should go check out the biochemistry of glycolysis. As you move through, you have a 6-carbon chain that is reduced to 2 3-carbon fragments, right? DAP and GAP, right? DAP and GAP that move forward in glycolysis. Does everyone know what I'm talking about? Yes? Okay, great. That's a reverse aldol. Okay? That's a reverse aldol, meaning it starts from something like a beta hydroxy ketone or aldehyde that reverses through to create then the donor and the acceptor. And try and see if you can see that in there. Because one of the we start here, but this is what you see in biochemistry when you're asked to know the actual reactions of metabolism. This is one thing you're asked to do, is to show all of these reactions via organic chemistry, but in the biochemistry realm, or in the biological realm, okay? So the reversibility is a possibility, okay? The reversibility is a possibility here. But this is the end of the line here. This is the beta hydroxy ketoneraldehyde, right? All I need to do at this point is add, well, there is water already present. So people have been asking this a lot, right? I added OH minus, and OH minus comes from sodium hydroxide or potassium hydroxide. Does anyone know what form those come in?
Solids?
They're solids, right? So what do I need to do with them?
Dissolve
Them in
water.
water. So water is always present when you have base. It's pretty hard, right? I mean, unless you get up and you make a really, really basic solution, there's still always some water there, right? So in this case, you can protonate your end material here with the water that exists. So this is the end of the line here, is the beta hydroxy ketoneraldehyde, right? So that's what we always get. We always proceed through a beta hydroxy ketoneraldehyde, okay? So that's your first step on the way. You can see the hydroxy position was the acceptor, right? Was the electrophile in the reaction, okay? That's where the hydroxy group came from. It came from the acceptor site, and the donor site actually came from the alpha site. So if I heat this reaction up, I actually see then the ability to run an E2 elimination. This E2 elimination is not common, okay? Someone tell me what isn't common about what I've just done. Why wouldn't this be something that you would have done up to this point in time? What's the problem with this?
Just strong base.
There's no steric hindrance.
Strong base.
It's a strong base. Strong bases are good.
But it's small.
Not a good leader.
Double bond on the carbon is good because it'll be a conjugated system, right? That's the driving force here, people. If you haven't recognized, I haven't said it yet, but it's the conjugated nature of that double bond that you're creating makes for a very stable system. That's what we started our semester with, right? Understanding that conjugated systems are more stable than simplistic vanillic systems. So it's nothing to do with resonance or the alkene forming or steric hindrance. So keep going. What else you got for me? Yeah.
Isn't the carbonyl carbon more electrophilic?
The carbonyl carbon is more electrophilic. Okay, that's a fair thing, but we know that hydration reactions still always sit to the left toward the ketone. Good, though. I like that answer. Yeah. It's the OH acting as a leaving group. And why is the OH able to act as a leaving group?
Basic conditions.
Because I'm in basic conditions. Exactly. Okay. So in this case, you don't have, oops, I added, oh no, that's right. You don't have much reversibility associated with this, right? Because in order to reverse this reaction, you need some acid to capture that alkene, right? So there isn't much reversibility associated with this reaction. The driving force, again, is the conjugation. The conjugation is the conjugated nature of these systems, which is a thermodynamic driving force for these reactions, okay? So when we call these alpha-beta unsaturated, in essence, this was the alpha site to the donor, right? The beta site was the acceptor atom. Okay? I say this a lot because you need to be able to work backwards through these in order, work forwards and backwards through them. So everyone understand what I mean? Yeah? This is the one that needs heat to go through. Yes, you generally will see base, and then step 3 or 4 or whatever is the next step, the next subsequent step would say heat. This is what's happening. Okay? Or see that. Yeah?
Is that the most acidic proton on the molecule, or are there more acidic
Yes.
protons?
No, that is the most acidic proton in the molecule. So it would still have to be on the alpha site, right?
Okay.
Yep. Sam sandwiched between those two oxygens. Okay, all right, so this is self-condensation. And self-condensation, we can begin to run into problems with self-condensation, right? This is a simplistic molecule, this is a symmetric molecule, and self-condensation seems pretty obviously okay with this type of molecule. But if I went back to my 2-butanone that I had before, right? So now I've gone back and I've created this, okay? I'm about to erase a lot of this, rewrite it to some extent. If I come back and I now have 2-butanone, and I add some OH minus, not LDA, OH minus, what am I going to get?
Deprotonate the alpha site.
I can potentially get 2 carbon nucleophiles, right? 2 carbon nucleophiles. So probability dictates that if I can get 2 carbon nucleophiles, I can then have each of them serve as a donor, right, to the acceptor molecule, which is the intact version of said ketone or aldehyde. And now I'm working to more than a singular product, right? Everyone see the problem here? So self-condensation sort of moves away pretty rapidly. There'd be some cases where self-condensation would be fine, okay, without it, but in a lot of cases we need to be very careful about our self-condensation reactions. Okay? Yeah?
Isn't this the opposite of carbocation stability, so you want to commonly favor it?
Okay, so there is a favorability for sure, but the favorability isn't as great as you think because there's also that thermodynamic argument as well. So we have to be very careful about that. Yeah, the alpha beta unsaturated products you get are different as well. So there's a lot of variability there. Okay, so when we get into these cases where we can have these mixed bags, this is where we get into this mixed aldol, you have a couple choices. You either take a donor molecule and a singular acceptor, meaning it can't serve as a donor as well. So there's some that you can think of, like this is a classic case of something that is now an acceptor and never a donor. Everyone see why this molecule here that I've just drawn is an acceptor and never a donor. No alpha proton, right? Okay, so I can certainly run my mixed reactions with things that will only be acceptors, but those are few and far between, right? There's not going to be a lot of cases where we are desirable, right, of using a singular acceptor. So what we do past that is we actually run our reactions with a little bit more thought in them, and we go back to our concept of directed aldol formation. So I can direct the formation of one of these aldols by using my temperature conditions in LDA. And what's also perfect about LDA is as follows. It is complete 100% conversion, okay? Lithium diisopropylamine leads to the formation of an amine on the product side. So I get out here, okay, I get now an amine. This is the nucleophilic version, right, which looks like this. Okay, so when it deprotonates, it pulls the beta proton. It forms the neutral amine as the conjugate acid on the product side. And as I look at the pKa difference, this is 36 here on the right side. This guy over here was your 16 to 20. If I'm pulling this guy, it's probably more toward 20, right, instead of 16. So this reaction, in essence, sits to the right, correct? There's a 16 pKa difference here, 16 pKa unit difference. So this reaction sits to the right. So at the end of the reaction, I use my end because everything is always an ebbing and flowing, right? But at the end of the reaction, I expect pretty much close to 100% yield of this, right? I have no more intact acceptor around. There's no more of this around to do any self-condensation. That's the reason to use LDA, okay? But there's going to be no more around to do this. So now what I can do is, generally you do in the lab, is to create this enolate, and then to add in whatever it is you want as the acceptor molecule. And you add that in slowly so that you ensure a reaction where this is your donor and this is your acceptor, okay? It's the slow addition that actually ensures maintaining the proper roles that you're desirable of, okay? So what you see then is nucleophilic attack at this electrophilic center to form your tetrahedral intermediate, okay? And so what you get at the end of this is this guy here. Label all these carbons. Yeah.
In the book, the reaction always is listed with THF. Is there a reason? Are there any solvent issues with this? Or?
You know, THF is just a nice global solvent that keeps a lot of things, yeah. THF also has a nice low boiling point, so it allows for ease of refluxing, right? Because a lot of these reactions do need heat, and it's nice to reflux with solvents that have a lower boiling point, so they allow that to happen. Yeah. That's just a piece of it. Okay. So we know that this is our direct product, and you should be able to work down the line to your final product, which is the alpha beta unsaturated ketone or aldehyde. So in this case, the alpha beta unsaturated ketone or aldehyde will look like this. You will need heat, yes. I'm just working through to the product. That's exactly right. I didn't show protonation. I didn't show heat. I'm just saying, can you draw the final product? Yes. Okay. So, self-condensation, rare, but you can see it. Directed condensation is something you're going to see a lot of, right? The use of LDA to create the donor that you prefer. Adding an acceptor molecule that you desire to get to the alpha beta unsaturated product that is necessary along your synthetic continuum. Okay? The last piece before we look at a couple that we work backwards is to understand an intramolecular reaction, meaning the donor and the acceptor in the same molecule. Okay? The donor and the acceptor are in the same molecule. Yeah?
So adding stuff there, that's not just the same class as the LDA?
No. Nope, nope, nope. So you make it first, and then there's the special sort of addition glassware that you use to sort of grip it in. Okay. What do I get at the end of this reaction?
Aldehyde. Two aldehydes.
Yeah.
The ring's going to break and it's going to give two aldehydes?
The ring's going to break in half and I'm going to get two aldehydes. That's exactly right. So the end of this reaction looks something like this. spot. Remember that reaction? Be very useful to you.
Hint, hint.
Okay.
Is the DMS the thing that makes it an aldehyde?
Okay.
It's a solvent. It's just an aldehyde.
So now we add some base, reflux, collect our product. What is it going to look like? Wouldn't matter, because the symmetry in the system, where I create my nucleophilic carbon, right? It could be this carbon here, or it could be this carbon here. Either of those, right? They're the same. So in this case then, let's just say this is it. This is the one that I create. This is my donor, my nucleophile. And this is my electrophilic center or my acceptor. Okay? And my donor and acceptor are in the same molecule. So you expect a cyclization reaction, right? Whenever your donor and acceptor, your nucleophile and electrophile are in the same molecule, you're expecting an intramolecular reaction or a cyclization reaction, where you get something like this. Nucleophilic attack at the electrophilic center in your molecule. And you could be so, logical as just to count, right? Count out the number of carbons you're going to get in the ring that you create. In this case, this donor will be one end of the ring, right, connected to this atom here. Anything that intervenes between those two slots is part of the ring, right? So 1, 2, 3, 4, 5. A 5-membered ring is what you're going to create. Remember, donor to acceptor, and any intervening carbons are going to be contained within that cyclic system. So in the end, you're going to get your O- off of here, and your donor is going to contain that carbonyl group off of the back end, right? If I were to letter this, okay, you in essence have now something like this. The letters help some people. I realize they can be a hindrance to others. But this is, in essence, what you get. Okay? And your alpha beta, so this would be at the end of really not even step 1. We're not even quite there. We need to first protonate to give me the beta hydroxy ketoneraldehyde, which is this. And then after the heat has been added, you're going to get to your alpha beta unsaturated ketoneraldehyde, which is this guy here. Want to see that? Yes? Yes?
Do you use water to protonate the O's?
You use water to protonate the O. Yes, you do. Other questions? Yeah.
Why is heat in the second step and not just one step altogether?
Generally, that's just what you see. I don't know. That's a good question. I mean, I think they're mixed, and then you heat it, but it's not like you wait to add the base until the heat is on. That's a good question. There's probably a reason for that. Okay. So we talked about all these in the forward sense. I'm going to put on 2 alpha beta unsaturated ketones or aldehydes, and I want you to work back and tell me what the donor and acceptor were and what reaction conditions you needed to get to said donor or to get to said product. Okay? So here are 2 that I worked through already. See what you get. What am I?
One of the original ones.
Okay. So to work backwards through these, you would in essence find your carbonyl. Okay? That's the first place I'm going to go. I'm going to aim right in for the carbonyl. And I'm going to look for my double bond or my OH group. Obviously I see a double bond and not an OH. So I know I'm going to start labeling from my carbonyl toward my double bond. So the alpha, beta. Okay? Now you can certainly break it apart from here, but I'm going to go so far as to go back and create the beta hydroxy just so we see it a little bit more clearly. If I come back one step here, I would create now the beta hydroxy version, okay? Keeping my labeling alpha and beta, okay? Now I see exactly where my acceptor was. It was the beta site, right? So this was my acceptor. My donor site was the alpha site. That is always true, okay? This is a given. The beta site was your acceptor site. The alpha site was your donor site. This, in essence, was your new bond that was created in the course of the reaction. Now you're able to separate them into two pieces. To the left of my solid, line that's breaking that bond is my acceptor, right? This looks something like this. It's my acceptor. Everyone see that? The OH came from the carbonyl. I know it did because it attacked an aldehyde or a ketone, right? That's how the OH manifests itself. To the right of my solid line is where I see my donor, okay? And that was this guy here. This specific atom was the one that did the attack. So you could check, right? You could check by doing the attack in the forward direction and ensuring that you're going to get to this product, okay? But if you do enough practice, you should write into this as your donor and this piece as your acceptor, right? And so now, what does that mean? How did I create this? What did I need to do? LDA at
Low temperature.
low temperature, right? LDA at low temperature. And then step 2, I add this molecule, right? And step 3, I heat it. Okay? So all together, I would start with that molecule. And I would say I take that molecule and add LDA at low temperature. So my synthesis is going to look like this.
What you're trying to do is take that anion and use that to attack the carbon
2,
acceptor.
I'm going to write out exactly the acceptor that was necessary to create that aldol condensation product. And 3, I'm going to show that some heat is necessary in order to move on to the alpha beta unsaturated product that I have. Does everyone see that? Okay. The molecule on the right has a distractor, right? It has that other alkene there. But I'm telling you, hone right into that carbonyl. You all want to look for the double bonds? Don't look for the double bonds. Look for the carbonyl, okay? Here's the carbonyl. This is it. This has got to be my alpha and beta site. This is my alpha and beta site, okay? So, I now can think backwards, and you don't have to do this after a while. I'm just doing it as a teaching element, but you could certainly write out your beta hydroxy molecule so that you see the donor and the acceptor a little bit more clearly. But the beta site was always the carbonyl. The alpha site was always the nucleophilic carbon, the alpha site, right? So this is my bond that was formed in the intramolecular aldol condensation reaction, okay? And so all I have to do is swing it out and around. Hopefully you can see that. Okay? Everyone see that? Now, let's just think for a second. This then was the site, right? This was the donor site right here. Why not this one? Why no this alpha carbon? It would have made a smaller ring. Bingo, that's it. What size rings are you aiming for? 5 and 6. Don't go for 3. That's a no. Don't go for 4. Don't go for 7. Find your 5 and 6 membered rings because those are thermodynamically favored. Okay? Understand that piece? No 3-membered rings. Okay? Which is exactly what this would have made, right? 1, 2, a 3-membered ring. All right, are there any questions about this? If there are, you'll find me in my office. We'll start with Claisen condensation on Wednesday.
I can